we have for the Allen Bradley PLCs, RS logics. How many types of timers do we have? And a lot of people got confused on that. I don't know if it was timers or counters, but they got totally confused on the types of counters. And somebody said it was coil timers. Those are not types of counters. Those are just ways we implement the types of counters, right? You understand? That would be like me saying, what's the types of vehicles we have out there? And you said red, green, blue. That's not a type of vehicle. That's okay. So the types of counters that we have available, and it even says it in the textbook, and it says it on the PowerPoint slide. So when I gave that out, we had people said single coil timers, coil timers, block timers. Those are not types of timers, right? You understand? Those are yeah, that's the types of counters we can have. Timers, yeah, sorry. What's the types of timers we have available to us? No, we don't have one shot available. We have what we call we have an on delay, off delay. These are what we call non-retentive timers. And then we have a on delay retentive timer, right? So technically we'd say a retentive on delay, I'm sorry, a non-retentive on delay, a non-retentive off delay, and then a retentive on delay. So what's the difference between a retentive timer and a non-retentive timer? Yeah, even when it's disabled, right? Understand that. What about and what do we have to do with a retentive timer that we don't have to do with non-retentive timer? Yeah, we have to reset it. So if we want it to start timing again, a retentive timer, we have to reset. A non-retentive timer automatically resets when it finally hits its time value, right? Or understand? Or when it's disabled, right? Everybody okay? Now, what type of counters do we have available with RS logic? Yeah, count up and count down. That's the only two that we have. We don't have a combination counter. There is another type that you'll run into there, which is the count up, count down. So it'll have multiple inputs. It'll have a count up and a count down input on both, right? You understand? But all our timers and all our counters are what we refer to as single input counters and single input timers. So we do two things with that single input. We use it as an enable, and we use it as a count input or a time input, right? Does that make sense? Are we okay? Then what we do, once we do that, we have what we refer to as registers. So what registers do we have available in our timers? Preset register, accumulator register, time base. We got a time base. And then we have what we call a status register or a flag register. Right? The status register and the flag. A lot of people that's dealt with microprocessors, we call them flag registers, because they're only single bit and they're either 1 or 0. And what they do is they set when what they look for is true, and they reset when what they look for is false. Does that make sense? And that's why they got the name flag. So it's flagging when it's true, right? You understand that? So what flag registers do we have for our timers? Let me bring up timer timing, timer enable, timer done. Huh? Move is not a timer instruction. Move is a separate instruction. Yeah, it's a separate instruction. So what's the difference between the timer timing and the timer enable? Yeah, anytime that rung is true, and this is where we had some conflicts in that test, and I redid that, right? I relettered that on the PLC1 test, is that it said if you wanted to see when the timer was active, which is kind of misleading, right? Because a lot of people say, well, when the timer is active, it's actually timing, right? You understand? So we have what we call a timer timing, and then we have a timer enable. Now, what's the difference between a timer timing and a timer enable?
The timer timing, wow.
Right. And then the enable, anytime it's true, right? Anytime the rung is true, then the timer enable would be true. Y'all understand the difference? But the way that question was worded, when it says anytime the timer is active, you didn't really know if they was talking about timing or timing enable. So I redid that question. We dropped it off. I dropped it off. I don't know if it was on the file or not, but it shouldn't have been. So whoever teaches the class next, they'll that question, if they use my test, the question should be taken care of. I think it's worded at if we want an indication if the timer was enabled, which one would we use? Or I think that's where we were.
Are you going to be teaching again?
I teach what they say. I teach what I have to teach. So PowerPoints. And so we went back just about over all the stuff. Y'all got any questions about how we set up the computer? The computer. So if I hook up a new PLC, what's the first thing we need to do? Establish a communication with the PLC. Once we've established a communication, and once we open up a new program, some of them call a project, by the way. So when you get into Siemens, I think they called it a project. I think Allen Bradley calls it a new program. Then what's the first thing you have to do when you start a new program? Yeah, you select the processor. Now, if it's a rack or a modular PLC, then you have to tell the application what rack you have, right? So we specify the number of slots, and then we specify what type of modules we have in each slot. So our 504s, SIG 504s is a 7 slot rack, right? You understand that. And currently we have a 16-bit input in slot number 1, and then we have a 32-bit output in slot 2, right? And then what's in slot 0? The CPU, right? And on a rack-mounted PLC, the power supply does not occupy a slot. On some of your fixed PLCs, it does. So you have to be, well, that's not really true. It's it's kind of misleading, and we'll have to look at that. So what we would do on our addressing is we have to the addressing, we have to specify what? First of all, we specify the type of instruction, right? Input or output. And then we have to specify what? The slot number. And then the other one is optional. So how does it go? Yeah, so what we would do is, and this would only apply if you got, so this would only apply if you got a multi-word module, right? So normally what we do is we start off with, and I think they put eggs, which would be what? Yeah, this would be the type of instruction, which is going to be examine if closed or examine if open, right? I understand that. And then we would put a what? Colon. And then what comes next? Yeah, next comes is the slot number. And then the next one is optional, right? You understand? If we have multiple words in a single module, then we would put a dot, right? You understand? And then we would put what? Yeah, the word number, word address. I guess it'd be more precisely. 0 or 1. Yeah. I've never seen an Allen Bradley module that has over 32 inputs on there, 32 outputs. I'm not saying they're out there. We might go look and see if there's that possibility. I think we've got a manual on the 500 series that tells us the different modules that's available for the thing. But if it's a 32-bit module, then you'd use 0 for the first 32 bits, and you'd use 1 for the second 32 bits, right? Does that make sense? Huh? I'm sorry, 16 bits. Then we would put a what? Slash, and then we put the bit number, right? Or the bit address. Now, if we don't have a word, then we would look like this. It would be X, and then it'd be what? Then I'm going to put a little X, and then we put a slash, and then we would put this. That's if we don't have a multi, and that's what we use in this lab. But you do need the format because you might run into one of these Allen Bradley PLCs. We got 16 inputs, but when you get into a sure enough control system, you're going to run into more than this, right? Does that make sense? Now this is our data file types. So we use O to represent what? Outputs. We use I to represent inputs. We're going to use S to specify the status register. Now the status register and the flag register are not exactly the same. The status register is the status of the PLC. And then the flag register, and if we differentiate to those, an instruction status register is the status of the instruction, right? You understand? So this status register here is not the status of an instruction. This is the status of the PLC. So this will show us where our faults are at. If we got a fault, we go in there and look at the fault number, right? You understand? Then B, these are our what? Bit registers, and we might have B3 or B10, right? Used primarily for what? Internal relays. And then T are our what? Timer. So we'll go a little bit. So O is okay and I is okay. But when I come up on the status register is actually S4. But what's nice is we only have one status register. So in our instructions, if we want the status register, we can just specify an S. And we can put a colon. So this would actually be the instruction right here. But we can access bits in our status register, which is pretty neat. We got one register in there that we'll use often, and I'll show you that once I hook up one of my PLCs. Then we have our counter registers. So T is actually what? So bits we either use B3. I wish they would have put this, or if it's available, we'll use a B10, right? What determines on all your Allen Bradley PLCs that I've ever seen, you have a B3. The B10 register is depending on the PLC itself. And that's what you're doing when you tell RS Logix your model number of your PLC, then that's going to establish what instructions you actually get in RS Logix, right? You understand? It's just like on your time base. They say that we have a 1, we have a 0.1, we have a 0.01, and a 0.001, right? Or do we have I'd have to look at that. But it all depends on what? On the PLC. So T is what? T what? T4, right? Counters are what? C5. Register is, and this is what's over here, guys. I'm sorry, I said B4, but it's actually B2. That's what they're telling us over here. Huh? S2, I'm sorry. Yeah, then you would establish a bit in the status register, or a byte in the status register. So it all depends what we're trying to do. There's one of the registers in the status register is a timing register, which is really neat. I think we established back we could set up 2 timers. We could go back and forth, back and forth, back and forth. In actuality, you don't have to do 2 I'll show you that one. So our control register is going to be a what? R6, right? Our integer register is going to be what? N7. And what's an integer? What's that? Yeah, it's a whole number, but it's also, it's a number without a fraction, right? I understand that. Unfortunately, the range of our real numbers are, what's the range? Anybody remember? Who said that? Captain? Sort of. You're close. So, yeah, he's the man. So we have plus ranges from 32,767, and then our negative range is 37,768. Now, why do we have one more positive number than we have? Why do we have one more negative number than we have positive? Yeah, 0 occupies one of the positive slots, right? So this is the range for our counters. So if you got an up counter, the maximum that sucker can one counter can count up to would be what? 37,000, and then it would roll over. So we have another flag that we didn't say because we didn't use it. We have an overflow flag that's available for our counters. An overflow flag would tell us that we exceeded what? 37,767, right? Because if you go past 37,767, what would be the next count? -1. A -1. So the counter would flip over to a -1. So we gotta understand that, right? Understand. So we can monitor that and see when it happens. So the overflow we go as soon as it's converted to negative. Then we have another flag we didn't talk about over here called the underflow flag. So an overflow flag we would use for positive count, for up counters. The underflow flag we would use for negative counters. And this would tell us as soon as we get past 37,768. Right, you understand that? And then what would happen if you want more, it would go to a positive number. It would go to a positive 1. So what do we call this flag? Overflow. And if we want to access it, then we'd use, what do you think they call the flag? OB. If we wanted to access this flag, we would call it what? UV. Yeah, underflow. So the negative, we have an underflow flag. The down counter, we have an underflow flag, and then the up counter, we have an overflow flag. Now, does that mean you can't count further than 37,767? We just can use more than one counter, right? We did that once where we had one counter set to 10, and then we would implement the next counter every time it counted to 10. So we were counting in tens, right? You understand that? So we did that in class. So if my first counter my second counter had a 1 in it, and my third counter had a 5 in it, then we've actually counted to 15, right? Y'all understand that? So we could set up our first counter to count to hundreds and then implement the next counter. And then later on when we learn, we got a command that we can multiply the two together. So what I could do, and we could use floating point numbers instead of integer numbers. So if I use floating point numbers, I can't remember what the limit is. I don't know if the book tells us or not. So that means we would be counting. Y'all understand what I'm saying? So if I started, this first counter counted to 100, and then every time this thing implemented by 100, then I could take my first counter and multiply it by the second. I can take the second counter and multiply it by 100, and that would tell me what? take my first counter, multiply it by 100, and that would give me my number. Right? You understand what I'm saying? So we can use multiple counters to count to exceed this range.
So you're saying first count counts for the number, second count how many times you use that number.
Yeah, and all we have to do would take the first counter and multiply it by the second counter, right? You understand what I'm saying?
Yeah, 'cause that confuses.
That would be one thing. So we can increase the range of our count. So the problem we have is that if I'm in a company and I'm trying to keep up with the number of vehicles I run or items that I run in a day, and we're sending out these, I don't think y'all seen some of these can factories that put out these cans, and them suckers are flying by. I could easily exceed this number in a day, right? You understand that? Or I might need to know the number that I have in a week. Well, if that means I would be messed up if every time I got up to 37,767, it did what? It rolled over. You wouldn't know. But what we could do is we could constantly reset the first counter, right? You understand? So every time it got up, what it would do is it would increment the next one and reset itself, and then it would start counting again. And then all I'd have to do to figure out my total count is I would take my second count, whatever I use for my second counter, that would be my multiplier, right? Does that make sense? And then multiply it by what? First counter, and then keep that in a floating point number, not an integer number. If I keep it in an integer number, I'm going to be limited to the sign numbers anyway. Floating point numbers, I need to look that up. I got it somewhere, guys. I think it's in the glossary. I think I put them in there. I mean, but it is huge.
So where is the floating point number at?
The floating point number is F8. You know what you mean?
You were saying that you just mentioned that the floating number was kept somewhere. So once you do the multiplier, then
you'd store it in an F register instead of an N register.
Okay. Oh, well, that's the whole point.
Yeah. That makes sense?
Mm-hmm.
So we can easily exceed this range with our counters just by doing what? Cascading counters. These are counters. Floating point numbers, right? This is the F8 register. I've never used the user defined. We'll have to see exactly what that is later on. It might be for multiple ladders is probably what it is. Are we okay? So we don't have to specify this for outputs, and we don't have to specify this for inputs, right? Everybody understand that? But everything after that, except for S2, believe it or not, it's the S2 register is that's what the actual address is. But we can also address that one with the S2 just by itself. Okay, you understand? Yes, no? So we added 2 additional bits. I think it was in the PowerPoints, but we were running out of time, so we skipped over a lot of stuff that I knew we would have time to come in and pick up at the first of this class because we review anyway. So this connection right here is what Allen Bradley. This connection right here is what is this? DH 485, right? Yeah, which uses the pin out for an RS-232, except for this connector on here. I don't know how many pins on it. This is called a DIN connector, this round connector that's key. How many pins, and then that will tell you how many pins are available on that. What's that? I didn't know it was powered up, is it? Okay. It'll be okay. We'll also show you how to configure the Ethernet IP that's on the side of Allen Bradley too. Are we okay? It'll be okay. These are the symbols for mechanical timers, right? You understand that? And if it points up, what does that mean? On the leg. If the arrow points down, it's what? Off the Now, why do you need to know these?
At least we're going
To know which kind of
Because
timer.
we're just saying, why do we need to know these? That's the wrong answer. Huh?
You could run out of timers on your PLC.
No, that's, well, when we draw the connection for the input and the output ports, when we draw what we have connected to those inputs and output ports, so we have two drawings that we have in a PLC program. We have the PLC program itself, which has a lot fewer symbols. And then we have the way we connect devices to the actual inputs, right? You understand? So what are we supposed to use on those drawings? We're supposed to use the electrical control symbols, right? You understand that? So if I've got an outside timer connected to the input of one of my inputs, I'm supposed to use one of these symbols. Y'all understand? Yes or no? So on the input and the output side, you are in electrical controls, right? On inside the PLC, you're using either examine if open, examine if closed, or then these other things that's available to us. So, y'all understand? So this is a normally open, time closed. This is a normally closed, time open. Right? This is a normally open, timed open. This is a normally closed, time closed. Did you hear the way I said that?
Before you go to the next page, let me get this stuff.
Sure, it's up on Blackboard.
Yeah,
Say normally closed.
that's for in class.
Yeah, what we do on the timers, the nomenclature that we use on electrical controls, we don't say on delay and off delay. We'll come up here and we'll say this is normally open, timed closed. So that means when it energizes, it's going to time to what? To close.
Okay.
We would say this, normally closed, timed open. Down here, we would call this a normally opened, timed open. We would call this a normally closed, timed close. So you see on the off delay, we say the same thing both times. So we say it's normally open, timed open. So that means this guy's going to close instantly, right? You understand that? And then when you turn the timer off, it's going to do what? It's going to time open, right? Does that make sense? So this is the way these guys are going to be nomenclatured or named. Normally open, time, and so notice your on delay timer, they're opposite. Your off delay timer, they're what? The same. You understand what I'm saying? So right here, there's an O, and right here, there's a C. Right here, there's a C. Right here, there's an O. Right here, there's an O. Right here, there's an O. Right here, there's a C. Right here, there's a C. So that's what we're saying. Understand? So that's the way we nomenclature in motor controls or in electrical controls. Are we okay? Move on. Of course, we know about on delay and off delay. So tell me the difference between an on delay timer and off delay timer.
on delay, energize, off delay.
Well, I can energize and de-energize both of them. I don't know if I understood what you're saying. Maybe I didn't hear.
The on delay has to be energized to time. No?
Off delay time is waiting on the de-energize. On delay is waiting to energize.
Well, you probably know exactly what you're saying. The on delay timer times when it's energized.
Right.
The off delay timer times when it's de-energized. Or when the rung is in another term that we use. So energize is a term that we use in motor controls. We don't say rung is true and rung is false. In PLCs, we could probably use those interchangeably, right? You understand? So we could also say the on delay timer times when the rung is true, and the off delay timer times when the rung is what? False. Are we okay?
Yeah.
And this is true. So then we have another type of on delay timer. So we have two types of on delay timers. We have retentive and non-retentive. Starts timing when the timer coil is energized. So here they're saying timer coil is energized. That would probably be, but you need to understand this cross, I don't know how to say it. What we're dealing with is we're dealing with people who come through two different technologies, right? You understand that? So in motor controls, this is what we would say. So in electrical controls, we would use the term energized, right? You understand that? So what that means is that the rung is what? True. Everybody understand?
You're
Yeah.
saying energized remote control is true for PLCs.
Well, either one. The problem is when you get into PLCs, you're going to have people say energized, and you're going to have people say true. So either one is true in PLCs. In motor controls or electrical controls, I've never heard anybody say the rung is true. I've never heard that. But in PLCs, you're going to have electricians that's definitely going to call it what? Energized. Then you're going to run into people that's came up through digital, and odds are they're going to probably say what? True. But it's up to you to be able to interpret those. Say, well, I wish they didn't do that. Well, guess what? You don't have, yeah, they do. You don't have any control of it. Normally open contacts close and normally closed contacts open. So here, the only time that we really get concerned with examine on and examine off guys is on that stop button. Normally after that, we almost always just use this guy right here. Normally closed and normally open, right? You understand that? So if I've got an internal relay, or if I'm using a normally open contact from a coil, when that coil is energized, that contact is closed. And when that coil is de-energized, that contact is open. If it's inside there, right? You understand. But when I'm coming from an input, from an actual physical input device, that's where you're concerned with the what? Examine open and examine closed. Right? You understand? Good. Yeah, but when you're inside the PLC, so if I'm using a contact that comes from even an output coil, if I'm using a contact down here, which is considered to be an input, right? You understand that? Even though it's controlled by a coil, it's still considered to be an input or a control device. If that coil is true or energized, that normally open contact will be what? Closed. If it's false, a normally open contact would be what? Open, right? If it's a normally closed contact, if that coil is energized, it's going to be open. If that contact is de-energized, it's going to be closed, right? So the only time you're really concerned with that, examine if open, examine if closed, if you're dealing with that stop button. Or it depends on if you're dealing with sensors, it depends on what that sensor gives you back when it's true. Does that make sense? Yeah. So normally sensors give us back a voltage when they're true, and they give us a voltage, no voltage or 0 volts when they're false. But that's only true if they have two outputs. We do have sensors out there that are we call them 4-wire sensors that provides a normally open and a normally closed contact. So that's where you got to be kind of careful depending on which one of those contacts you use on those sensors. Does that make sense? So this is what they're saying here. So your timer has two coils out there that it represents. Let's see if we get a picture in the diagram. So the two coils that it represents is this guy called enable. And then it's got another coil called what? Done. And for some reason, don't ask me why, they don't attach the done to L2. But the enable is connected to L2. And now why they do that? I don't know. So when we say energize, they're talking about the timer. They're not talking about these guys over here, right? So to energize this timer, what would I have to do? Yeah, this switch or this push button or whatever it is would have to be, or this sensor. So we say switch, but over there on the line, this is just an input. What could it do? Anything. Could be anything that provides us a 1 or a 0, right? You understand that? So it could be a sensor, it could be a push button, it could be a switch, right? It's going to be, I understand that. And that's what we was looking at over there. So this doesn't define it as a switch. All this defines it as some device out there that is going to give me a 1 when it's true and a 0 when it's false. And it's going to be outside of the PLC. Everybody understand that? And that when they say energize, they're talking about this guy right here. They're not talking about these guys over here, right? You understand? Even though this guy will tell us what when it's energized. By the way, I think if you look, when it's timing, this turns into TT instead of enable, I think. Everybody okay? The move instruction, everybody okay on that? What can we do with the move instruction? Very powerful instruction.
Or no, is that when you started new?
The example they use in the book is that we have two different things we need to do on this timer. We either want to time to this value or we want to time to another value. Well, the problem is if I set this preset up as a constant, then whatever I put in my preset register, that's all we got. Everybody understand that? That makes sense? No. Tell me what don't make sense. If I enter a number in this preset register, it is a constant. And what is a constant? We can change it. We can change it. It's just I have to change the program. So a constant is not something that can't be changed in PLCs. A constant is something usually that I have to change the program to change it, right? Understand? So up here in that first one, I've got a move instruction. And what register is it addressing? It's addressing the 16-bit preset register. So the preset register is a 16-bit register, right, or word. So it said, okay, what's it going to say? My source is what? 1000. If I press that button right there, the move is going to move my source into my what? Destination. Which is going to come in here and change the preset value from 1500, from what? From whatever it was to what? 1000. Y'all understand that? This timer right here. Yep, yeah. So that's timer 4. Timer 4.0, 4:0, preset register. Everybody understand that? Okay. You okay? Now the green button is going to load the preset with 1000, right? You understand? The red push button is going to load the preset with what? 1500. Okay? Okay.
Press the green button once, twice, still going to be 1000. Press the red button once, still going to be not going to.
Well, once you press it once, then it'll preset every time. It holds that preset until you change it.
No, I don't count up.
Huh?
You just gonna count up like 2000 every time. It's gonna add 1000.
No.
It just goes to that value.
Yeah.
Yeah, but what you have to understand is my source. So here my source is a what? My source is a constant. That's what I was looking for. But my source could be a what?
It could be changed to whatever you want.
Yeah, but here it's a constant, and I think I showed y'all that. What y'all decide to do about lunch?
5,
Huh?
5,
Okay. So what I'm going to do here is I'm going to bring up a Logic Pro somewhere here. And then I'm going to come up and set up a simple circuit. What I like about Logic Pro is it's got a ton of inputs and a ton of outputs. It would be hard for us to do this with our PLCs. So even though this guy here's got 32 inputs, 16 inputs, we only have 8 switches to work with. Make sense? So we're basically wasting a lot. So what I'm gonna do is I'm gonna come up here and we'll just put a switch. And what I'm gonna do over here is on my move instruction, where was that? Not math, one more over. Move. And here we'll use switch input :1/0. And what I'm going to do on my inputs, I'm going to come over and look at the inputs that's available to us. So I'm going to bring up my IO inputs, and this is what I really like about this guy. So this is what we got. Okay. So this is input 5, and these are a bunch of thumb switches. So this is going to give us a decimal. I think they're BCD. We'll find out. Let me go through the values here real quick. Yeah. So what I'm going to do is I'm going to come over here and I'm going to come over here on my source. Instead of making a constant, I'm going to say I'm going to input from 5, and then I have to put that. Okay, so I'm going to put that right there. And then I'm going to come over here and I'm going to say move, destination is going to be timer 4:0. And then we'll come.
Colon 5.
Yeah, colon 5, because it's the whole 16-bit input that I'm going to do. Yeah. So what we're going to do here, and this is the power of the move instruction. So where's my timer? Yeah. So we could input a binary, but we got another instruction that we'll talk about later on. That I can convert binary over to BCD. We'll show you that later. And this will be my timer, so we'll come up here and put another switch up here.
Oh, it automatically gave you that wrong when you put the time down there, bring the end down.
Yeah, RS Logic does that for you.
Yeah,
But I'm sorry, Logic Pro does that for you, but RS Logic does not. So on RS Logic, you'll have to do it every time. You'll have to drag it down. So this is a really good simulation, but there's still a lot of problems with it. But you know, I've written programs before, and I'm very impressed with this guy. I mean, just everything that he had to consider when he did this. And here we'll use input :1/0. So what I'll do is over here, I'm going to make this a push button, and I'll leave this a switch. And I got to give this a time. Timer 4. Everything okay? 0. So here, if this thing works according to the way I think it's going to work, which I'm pretty sure it will, then we'll download it to our PLC, and then we'll switch it to run. So what I'm going to do is I'm going to come over here. I'm going to have to go back and forward, guys. So what do you want to put in the timer? Okay, so let's put that in there. And then what I'm going to do is I'm going to come back over here to my push button. And I'm going to hit the push button. Oh, we didn't put it right, sorry. Yeah, where's it going? Yeah, thank you. Yeah, so we got to put it in the preset register, which is right. You understand that? And it's a 16-bit register, so since it's a 16-bit register, I had to use a watt instead of a slash, a dot. You understand that? Thank you, guys. Looks like it considered it to be binary instead of BCD. So it took it to be binary, guys. But what I just did, so I didn't use BCD. So it brought it in and thought it was binary. I see what I'm talking about? Yeah, I didn't interpret it as BCD. It interpreted it as a binary number. And so we took that number and converted it and looked at binary. So what I'd have to do is I'd have to come up with another instruction that we can take my BCD and convert it, take binary and convert it into BCD, which we're not there yet. But what I can do now is I can come over here and do what? Yeah. So instead of using the switches, let's use these guys right here. And we'll change these to switches. And that way I won't have to keep going back and forth anyway. So we'll go offline and then we'll change it to input 3. Uh-huh. It's the whole byte. That's the whole word, I'm sorry. So we'll say I want to just figure something simple. I'm going to load it with 15. So I'll come over here and just put this to 15. And now I hit that button right there. And what did it go to? 15. So now what we've done, y'all understand? So what we've done is change this from a constant to a variable. It's actually 1.5. RS Logics, we don't have, we don't select the multiplier. By the way, the time base, you don't enter the time base. If it was over in Logic Pro, we hit a little, you hit on it, it'll drop down the strobe, and then you select the multiplier. RS Logic Pro doesn't support. This is the only time base that it supports. So this guy would actually time for 5 seconds, right? I'm sorry, 1.5. Oh, you'll see what I did. Nobody caught me on that either. Yeah, I got an address. Yeah, I did. That's why I made this on a switch. Why did it? Oh, I'm sorry, I'm not on run. So what I can do now is I can come up here and load it with anything I want to, right? And this is the power of the move instruction. So any of these, I can change the accumulator if I wanted to for some reason. The accumulator is addressed ACC. I can change the preset. Can't change the time base, right? You understand that? I can't change the time base. So the time base is a constant. I mean, once you select the time base, the only way you can change it is to go back and do what? Change the program. Okay. Let's see if the aim on this. Yeah. No, it doesn't change the timer time, and I thought it did. Okay, guys, let's take a 5-minute break. Huh?
Well, we don't really remember much of this stuff.
This is advanced. Because they took it.
We didn't learn all of it.
Well, this is advanced PLC. You didn't learn this.
No, I'm just talking about everything since you've been talking about in the morning with the distortion, all of that. All we learned was input. I'm lost. I'm lost. But you know, Brittany didn't teach all this. After a minute semester, she just made it do that. Like sources and.
Well, we can't go back and reteach everything. And unfortunately, I can't go back and reteach everything I was supposed to learn.
Well, see, look, I got everything. Like, I learned everything. The only thing I'm stuck on is, like, counters and timers.
Well, that's what we're going back and review.
But
So
I'm also
this is
stuck, like, on the preset, like, what all that means.
Well, I thought we just went over that.
Kinda.
Yeah, you did. It was powerful. We supposed to learn that.
Yeah.
I ain't never heard accumulator. How do you do this whole preset?
So,
Um,
I I'd probably be better, like, I could do it probably if I was on the PLC, like how you're doing it.
Yeah,
That's
we're
usually
fixing-
how I
we're
figured
fixing to
everything
go
out.
down there today.
Okay.
But one thing y'all need to make sure.
I don't even know how when you asked the class this connection, how everybody knew it was the RS2,
485.
whatever they said. But we never looked at
She didn't really teach.
it. Well, she didn't teach us.
She kind of
She
just
sat and read.
read book.
And then she made us do live like the last 4 weeks.
I don't know.
Like, that's all we did, like, the last 4 weeks, 4.5 weeks. Came to class and do lab.
Well,
That's
the
why-
course is supposed to be taught through timers and counters.
That-
And then
That's
we come
why,
back.
that's
And
why,
we did advanced timer and counter layout. That's what we start out, and then we go to math, and then we go to compare.
that's why, you know, that last semester I came in and asked you, is she supposed to be marking off points when asking questions for lab?
Oh, yeah, she
Well,
did
she does, and we do and we don't. Normally what we do is we go the first 4 weeks and we're really lax, and then the second 4 weeks is what we really start on.
You know, because that's the
Since she
problem
did
we
that,
had.
she should split it in between, well, I can't say what.
No, I'm just saying that's why we kept asking the last because we didn't understand what we wanted to do. I thought it was that right.
But y'all went in there and,
The only thing that she actually stood up and taught was the Boolean expression. That was my first time seeing the Boolean expression.
Oh yeah.
That's the only time that she actually stood.
I guess it's all gonna hit me in a minute. I don't know.
well, you
Kinda
know
already
there's
some
a
of the stuff.
path y'all should follow when you got any concerns. It's in the syllabus. There's a path you should follow. The first thing you're supposed to do is talk to the instructor. If you've done that, then you're okay. The next thing you need to do is you need to schedule an appointment with Ms. Wilson. And the third thing you need to do, if that don't resolve it, you need to go and do, there's a thing on Blackboard, not Blackboard, on the Boston State website where you're supposed to be going up there telling you about concerns that you have about the class. Now that's the way you're supposed to do it. And then we can do something, right? You understand?
Can I ask some questions real quick? Alright. T4.
That's the address of the time,
Alright, the 0 right here is
number of the time. So we can have.
number of the timers?
Yeah,
Oh,
so
timer
how many
is 0?
how many timers do you think you can have?
I guess several.
Okay, so how do we specify a different time? Well, what we do is every one of them starts out here.
Okay, so
And
0
then
would
we
be
use a
1.
number would be a timer. The next one might be 1, 2,
Okay.
3, 4.
Alright,
And
now
we
time.
can go all the way up to 255 depending on the PLC.
Right.
So RS
Remember
Logic supports that, but it don't mean you get that many. It depends on the actual PLC.
I remember that now.
And also counters. So C5, the first counter would be C50. And the next one I use is probably what?
1, 2, all the way to
255. If your PLC supports it, if your PLC supports it.
which
This-
we ain't gonna go that high.
No, we'll never go that high, but you don't have to start with 0. You know, you might have a timer that you want to time to 33. Well, you could call the timer number 33.
Right.
It's just that anytime you use the contact, you would have to remember
Yeah,
which timer.
which one.
Yeah. I mean, so you can use any of the addressing ranges. It depends on how much memory the PLC itself has. So, RS Logic supports this range right here, but it don't mean, so that's what you do when you go up there and tell the RS Logic what PLC you're using. It comes up and it says, well, this PLC can only do 15 timers, and then that way it won't let you do anything above that, right?
Alright, now time base.
Time base is a multiplier, that's all it is. So what we need to do is, we need to go in seconds, we might need to go in tenths of seconds, we might need to go in milliseconds. But what we do, like now, I got 31 in there. Well, the multiplier is 0.1. So my timer actually is times 1.3. Okay.
So at times faster.
Well, a timer, we have the ability to set a timer for different values, right? You understand? Yes or no?
Yes.
So this number I enter right here, this is an integer, which means it don't have a sign, so no fraction. But how would I time to 100 milliseconds? How would I time to 100 milliseconds?
the decimal.
Yeah, well, so we have is we have different multipliers. So we have 1, it depends. We have a 1. So if I put a 1 up there, if I can't do that, then that would be 31 seconds.
31 seconds.
If I put a 0.1, then it'd be 3 point seconds. If I put a 0.01, it would be 310 milliseconds, right? So while we enter this number right here, this is going to be an integer. No sign, no anything. And then I establish a time base, so I can time in milliseconds or whatever, right? Does that make sense?
And the accumulator is.
Accumulator keeps up with where it's at.
So it's counting the same time as
It's the timer. I can't change the multiplier, but I could change this value. So let's make this value bigger.
I got the time on.
Okay. So watch so I'm gonna load it, and then I'm gonna start the timer. But what you see, the timer contains the accumulated value. So it's gonna start counting at 95. It's gonna start counting at 0, and it's gonna start counting. It's gonna go up to 95. As soon as it hits 95, this guy right here is gonna say, "Well, I'm done." So watch it. Since we got a bigger number, you should be able to see it.
Okay.
So it's enabled. As soon as it hits 95, it's going to stop.
Yeah.
It says it's well,
Done.
done. So now we can use that done contact.
Could you use a timer timing cool right here
Must
instead of an enable?
Yeah, but enabled and timing is different. So right now, the timer is not timing.
Right.
Okay. So we don't see that coil, but I can use it somewhere. So I could come down here, so I've got it back on program, and then we'll put in another run.
I also want to ask about the move source. Like, what does it do?
Well, when I move something, what do? I take something that's here and put it there.
Right.
So I got two things. I got a source and a destination. So
Alright,
the source is what I'm moving. The destination is
You
where I'm,
labeled it I3.
yeah, that's input number 3. But since I didn't put a dash, it took the whole system. Since I didn't put a slash, I can the whole system bits. Understand?
Right.
So if I come over here and get this, if I output, first way y'all learn with input 3/1. Well, this address is a bit. If I say input code 3, then this gives me the whole word.
Okay. Yeah, she can fix those, but
Huh?
still, what's the point? Like, what are you moving?
I'm moving whatever I put on this input right here. So here's input 3. I'm taking whatever I put on this input and I'm putting it into the preset register of timer 4. So we can address these registers. So if I want to address this register, then I'm going to say timer 4, right? Then I'm going to give it the timer number. And then I'm going to put a dot, which means it's 16 bits. So a dot indicates 16 word. And then I come up here and I say preset. Well, this is the abbreviation for this register right here. Okay, you understand? Okay, so this is input 3. Okay, so what do y'all want to put on input 3? So I'm going to come over here and I'm going to put a 1 on input 3. I'm going to take off all these switches right there. This is Logic Pro. This is not RX Pro. It's a simulation. It's not this guy. This is a simulation. We like it because we got all these inputs. So see, I've got 16 inputs here. I have 16 inputs there, and I have 16 inputs over there on 5, and then I got all these outputs. So what I'm going to do now is I'm going to come over here and upload it. Is it already uploaded? No, I'm adding it. So what I'm going to use here, and then we'll come down here and put another rung. Come on. Oh. Yeah, but I got to get rid of this one. And what I'm gonna use here is I'm gonna say, okay, T4 colon, right? Colon 0 slash timer timing. Okay.
It's slowly coming back to me.
And then I'm gonna come right here. I'm gonna say T4 colon 0 slash timer done. I mean, I'm sorry, done. Yeah. Okay. And then we'll come up here and we'll put one more. And then we'll say, we'll call this T4 colon 0 slash enable. Yeah, well, what we're going to do is see the difference between these bits. Oh, I know what I'm doing. I'm touching two buttons at the same time. And then we'll assign these to some light so we can see them working, right?
Are you referring to what's in bits right there?
Yeah, those are bits. Those are one
Still
bit.
call them bits.
Yeah, they're either ones or zeros. They're bits. One digit. So these guys right here are bits, right? You understand? And then we can come up here and assign this to output colon 0 slash 0. I'm sorry, 2 slash 0. We can assign this to output colon 2 slash 1. And we can assign this to output colon 2 dash 2. Okay. And this right here. I'm listening.
No, but you put out a little O in it and it made it big.
Yeah, I tell you, and even RS Logics will do that for you. You don't have to use uppercase O's. You can use lowercase O's, and it automatically converts that over to you for you. Yeah. So we got it. Well, we'll shift it to run, and we'll put a number in here. Don't make any difference. Okay, so right now, yeah, I still had it. I still had the timer enabled. So, well, let's put something in here. Put a pretty big number. And then what can I do now? I can press this button right here. And what's this going to do? It's going to move 3, not 3 slash something. It's going to move 3. The whole 16 bits, right? And I'm going to come over here and I'm going to hit that. And where's it going to move it to? Timer 4, 0 into a dot means 16 bits or a word into the preset register. So as soon as I hit that, you see it? Okay.
Do it again.
I can't do it again.
Oh.
I done moved it. Well, this shows you what your source is. Where's the source coming from? It's coming from this guy over here.
Right.
Okay, you understand? Okay. And then I'm going to come over here and let my...
BCD, it's now binary?
Well, it never was BCD.
Oh, I thought you...
My switches were BCD, but when I used the move instruction, it interprets it to be binary.
Oh, okay.
Okay. So if I come up here and so what was happening was I come up here and I set my BCD switches to this, and then that would be this in BCD. But my move instruction saw it at 1, 2, 4, 8. It saw it at 16, right?
Okay.
So what I would have to do is, if I'm inputting for BCD switches, your PLC
Doesn't know that.
looks at it as binary. Yeah, it looks at it as binary. Unless you do what? Unless you have an instruction that you converted over to BCD. And we can do that.
Okay.
We just haven't got there yet. So if you look forward in your book, you would see there's a data where we can convert between BCD and binary and BCD, right? You understand that?
Okay.
We just haven't got that instruction yet. Okay, so what we're ready. So I've got a timer enabled, I got a timer timing, and I got a timer done, right? You understand that?
Right.
So notice as soon as I close this switch, the timer timing and the timer enable go true.
What switch?
I closed 1 + 1, so the timer started timing. right? So this is true because the timer's enabled. This is true because the timer's timed.
Right.
But the timer's not done.
No.
Now what happened? It's still what? Enabled, but it's not timing anymore.
Right.
It's done.
Yeah, and it's done. So that's the difference between the timer timing and the timer enabled. So as long as the rung is true, the timer enable is going to be true. Right? You understand that? Make sense?
A little bit.
And like I said, unfortunately, I can't change the multiplier and all that Logic Pro. Are we okay? So I can change whatever number you want to put in there, right? Y'all see this? Yes or no? So I come up here now, I've loaded it with another number, right? You understand. I start my timer. What's going to happen? Timer enable and timer timers are both come true, but timer done is not true. And then as soon as it finishes, the timer timing goes false, but the timer enable is still what? True, because literally the rung is enabled. So the timer enable is going to be true anytime the rung that's controlling the timer is what?
Energized.
Well,
It's
yeah,
true.
The whole run's got to be true. So if I put multiple input devices, no matter what they are, all those have to be in the right position to get the rung to be true. Y'all understand that? So when the rung is true, or when the timer's energized, those are perfect. Everybody okay? So what's nice about using the move instruction, and this is why, and unfortunately the book don't tell us this, is that we can use that move instruction to move a variable into a register. Now, as soon as I do this, it's no longer a constant, right? You understand? So my preset register can be a constant if I do what? If I set it, right? If I enter a value in there, or it can be a what? It can be a variable. Which makes it a variable. That makes sense. So the move instruction, we'll use that a lot. We'll probably have to use it a lot on Logic Pro than we did, because if I was going to do this, no, that's not true. We'll show y'all later on where we can cover up bits. We can do what we call mask bits. Mask bit means if I'm using some of my push buttons to control a circuit, and then I'm bringing in a number on, let's say I'm using 2 of them to control the circuit, and then I want to use the other 6 for variables, then we have the way of doing that. We have a way of stripping off what we don't want. We call them masks. And we'll learn how to do that in this class too. So this is also true on counters. So even on counters, I can access what? The registers. Yeah. You can't change the address. So I don't have access to this guy, but I have access to these 2 registers right here, right? That makes sense?
Unless you change the whole program, you're saying?
Unless you change the program. Yeah, you can change the counter. So how do we address those registers? Well, I'll start off with what? I'll start off with a timer, right? And then I'd say what? 4. And then this would be the what? Timer number. And then I'd put a dot because it's a 16-bit register I'm loading. I would use PRE for the what? Preset. Or I would use what? Good, yeah. I would use ACC if I wanted to load the accumulator. Or if I wanted to change the accumulator. Or if I wanted to access the accumulator. So we can access the accumulator and do math with it. So later on we'll learn that I could actually take this and add it to something else, right? You understand? Like we talked about a while ago. I can multiply these registers when we get into the math instruction. So these 2 registers right here are totally addressable, which means I can use them as constants or I can use them as what? Variables. Which is pretty neat. So what's a constant? That's a number. That's a number that you cannot change. The only way you can change it is by changing the program. A variable is a number that we can change without changing the program. So we actually change
Only
it.
by using the move construction? That's the only.
Yeah. Unfortunately, they won't let you go directly from an input into this guy right here. So if you're gonna use these registers as variables, you have to come through a move instruction. They will not let you load directly. Understand, I can't come down here in my preset register and say input 3. So this number right here, the preset has to be a number, right? You understand? So if I'm going to get to these registers right here, the accumulator or the preset, then I'm going to have to come through the move instruction. And that's also true on counters. So what registers do you think we have access to on counters? So what's our two types of counters? So what's the difference between a retentive timer and a non-retentive? Yeah, so notice anytime right here, so this guy, so I'm gonna come up here and disable it, and what's the first thing that happens on this guy right here? It resets, right? Y'all understand that? Yes or no? Yeah, this is a non-retentive timer. If I come up here for some reason, and well, we will start off. We will eventually. I'll use the same switch, so we can use the same input multiple times, right? And it's no error. This is where it's good to assign symbols. We don't do that in RS on Logic Pro. So we'll come up here and we'll put in not a retentive timer. And we'll call it P4:1 maybe, right? Be okay. Then what I'm going to do up here. Oops.
That's it. It's just one coincide with
What do you mean? I just want both of them to time at the same time, so we can see the difference. Okay, that's all I want. And then I'm gonna put a down drop, or try to put it down drop. So don't stick it in there where I don't want it. So the guys that took PLCs from Brittany, did y'all learn about down drops and stuff like that, right?
No.
So a down drop, what we can do, if this thing lets me do it, is we can y'all know the rules, right? Yeah.
Yeah.
It's fine. A branch is fine. Come on. There we go. It's going to let me do it. And then what I'm going to do is I'm going to come up here and put another move instruction. I do that all the time. I try to move the tab down there. And here what we're going to do is we're going to take the same value. So you can't do two things with one move instruction. I'm going to take input 3 now, same input. And where do I want to put this at? Well, I want to put it in my retentive timer. I'm going to put P4:1. P4:0:1.preset. Okay, we okay? Can y'all see what we're doing? So this is a retentive timer. This is a non-retentive timer. But what I want to do is I'm going to load the preset register with the same number so we can see the difference. Huh? No. You can't say totally it doesn't matter which one you put first. Technically it don't. Because remember, this thing starts scanning where? Yeah, here, then it comes down here and down here. So it might matter, but in our situation, it's not.
Does it show somewhere on there that it's retentive or not?
Yeah, RTO.
Oh, I'm sorry, yes, thank you.
Welcome. So we'll put a number in here. I don't know what it is. We'll go ahead and load it. But notice both counters loaded with the same number, right? Because this instruction moved it into the preset register of 0, timer 0. This moved it into the preset register of timer 1. Okay. And then when I come up here and close this switch, both these guys are going to start timing. Okay, so notice they're both timing. And they're going to get up to 64. Okay, now notice now they're both at 64, right? You understand? And what I'm going to do is I'm going to turn off my switch up here that's controlling my timer. Notice that. Notice my non-retentive timer went back to what?
It reset itself.
My retentive timer stayed at what? 64. Right, it stayed because it's what?
Sure.
It's done. So I could do this with this one. Notice I'm going to load it. I'm going to disable it. I'm going to load it. I'm going to disable it. I never.
So all I would have to do is energize it, and that first timer would continue.
Yeah, so let's come up here. We got to add one more feature to this thing. Yeah, these retentive timers, if we ever want them to go back to 0, and surely we will, then we need to add a what? I'm going to add it right below this so we can see it really.
So I just have to have a separate reset. So it sounds like using a non-retentive timer. When you use less steps.
It is, but you don't keep up with your time. Right? You understand?
Okay, yeah.
So there's some times where we want to stop and stay stopped for a little while, right? You understand? So, I'm over there doing something and something happens and I need to stop it. But I need to run this 15 seconds after this, right? You understand? So I stop my line, I make a correction. Well, a non-retentive timer, what did I just do? I lost my time. My retentive timer, I kept it, right? You understand? And then I could use the timer. I could use the timer done to reset it because it's only going to become true after 64. But what I could do is I could keep stopping it, right? You understand what I'm saying? So we'll change that over. We'll start off with just a regular push button. I need to put another rung in there. And then we'll change it over to the timer done. So we can reset it with the timer done. So what I'm going to do is I'm going to come over here and add another push button right now. Input, :1/2. And then we'll go back over to our timers and our counters. And then we'll put a reset instruction. So a reset instruction is considered a what? An input or an output? Output, because it moved to the right, right? And we're going to reset timer 4:1. Are we okay? So we'll use this guy right here, and I'll change it to a push button. And then we'll come up here and yeah, we have to reset it first. So let's download it first. That might work a little better. And then we'll run it. Now notice the retentive timer, even though I took it out of run, it was. Okay, yeah. So we'll start off first by resetting that guy. Okay. And so what we can do here is I'm going to load it. Okay. And then I'm going to come up here and start it, stop it, start it, stop it. Can you see what's happening every time? Every time every time I disable the non-retentive timer, it goes back to 0. Even though I'm disabling the retentive timer, it does what? It keeps this going. That's why it's called a retentive counter. So I come up here, enable it, disable it, enable it, disable it, enable it, disable it. So now I can go out there and do what? I might stop my line. I see something happen. I stop my line, but I still got to keep up with this time, right? You understand? And then I can do what? I can go out there, make my corrections, hit it up, and the timer would start off from where it was at. That's the retentive timer. The only problem with the retentive timer is I need to do what? Reset it. But we could come up here. So what I'm going to do now, I'm going to go offline. And then I'm going to go to this contact right here. Did I go offline? Let's not. Let me do anything. I did. Yeah, I'm gonna put it on the done. So I'm gonna say timer 4:1/, no, I don't want it to reset with 1. I want it to reset with itself, but only when it's what? When it's done, right? You understand? Yeah, so I'm gonna put people, and I'm gonna put done. Good, got it. Okay, so we'll download this, and that way I don't have to use a reset every time it finishes timing. It would automatically do what? Okay, I'm gonna come up here, download it, put it to run, load it with something, come up here and start the timer, stop it, start it, stop it, start it, stop it. Can you see what's happening? Okay, but watch what happens when it gets up to 64. It's gonna, yeah, it automatically reset. We probably need to figure out a way to stop it. But you can see how we could, yeah, you can see how we could do this, right? You understand? We're okay. So we could trigger this with something else. But now what we're doing is it's automatically doing what in time. And you never even see this. Why don't you see this go through? It happens so fast, right? You'll never see it.
So it's basically just made her 9 or 10 times.
No, it's not huh?
Yeah.
Well, this one still times at 64, so it's not quite a non-retentive timer because I can still do what?
You wanted it to reset, you do it where it resets only one of them, or no, it has to like continue to reset. But it's that too complicated and off lesson, don't we?
Well, probably not. It's probably off lesson, but what we could probably do is come up here and use multiple contacts. We just have to figure it out. So we might use the timer enable and the timer done, and we would see if it would meet a race and see what it would do. But yeah, we could do that.
Okay.
I'm sure we could figure it out. Are we okay? So y'all see the power of the move though, and y'all see the difference between a what? A retentive timer and and of course what else we needed was a what? An on delay timer.
The move has enabled us to do what?
Change a constant into a variable. This scenario. Now, the one they give you in the book, they're loading it with 2 constants, right? You understand? So we wouldn't consider those to be a variable because the move is using a constant and the other move is using a constant. So if I wanted to change those, I would have to do what? Change. A variable means we can change things without what? Without changing the program. Are we okay? And then, of course, an off delay timer. Are we okay on off delay timers? Let's go the wrong way, Rich. So we'll run this one off exactly the same thing. But instead of making an on delay timer, we'll make this an off delay timer. And of course, we got to give it a different address, right? T4:2 enough. Preset value. Well, let's go ahead and we'll just preset this one. We could add another move instruction. Everybody understand? So let's just make this 100.
Okay, most of the address is one move.
No, because all you got is a source and a destination. So that's all you got. So it'd be like moving couches. You go over and say, well, move that couch and that couch and that couch. You're going to do it what? One at a time. You know? So that's the same thing true here. So all we can only go, we only have one source and one destination that we can specify per move. And your source and destination are constant, which means you can't do what? I mean, these are not numbers anyway, but in your command, you got one source and one destination. If you want to move the same values or different values, you have to use different move instructions. So that's why we had to use 2 move instructions, because this is going to take this destination and move it into the preset of T40, right? This is going to take the same input word, right? The whole word. And he's going to move it into the preset register of T41, right? You understand that? If I wanted to do that with this one, then I would have to do what? I'd add a third move instruction, but understand what we could do. I could just put another down drop in here. I'll put another branch. I could put another down drop in here and do what? Put another move instruction. So I could do multiple moves with the same rung, right? You understand that? It's just I can only do one move per move instruction. That makes sense?
Isn't this where cascading fit in? Or no? Isn't that cascading in yet?
No, cascading is when you let one timer feed another timer.
Okay.
So I might use the done bit off this timer to feed this timer. We would use that. The book says increase the time of the timer, which is highly unlikely. Normally we would say, okay, I want to run a motor for 15 seconds, and then I want to stop it for 10 seconds, and then I want to run it reverse 18 seconds. Well, what we would do is we would start it with our first timer, and then when it finished, it would go to the next one and keep up with the stop time, and then it would go to the next one and keep up with the reverse time, and then we might repeat it. It depends. Normally, that's what we use multiple timers for, right? You understand? Because I can go up to, it's an integer, so I can go up to 37,700. So that's a big number for a timer. Now, if I can't get 37,700 seconds, then I needed a lot more, right? If I needed like 24 hours, then I would have to do what? I'd have to cascade this one to cascade timers. But normally what you see is that when we come up here and we use multiple timers, normally it's to do different timing things, right? You understand? Do this for so long, but let's do this one for so long, and let's do this for so long. That's for people that don't know what they're doing. What we'll find out later on is that we have ways that we can use one timer that times everything, and then we can set up this one to do it this long and this one to do it this time. So you can tell right off that. And like I said, that's what we're going to learn this semester. We're going to learn basically how to reduce rungs with more advanced commands. That was cascade timer to increase the time. To increase the time. Increase the time available. Yeah. That was what it was in PLC 1. So that's about the only time we would cascade timers. But you got to understand that the explanation they used is I took one that was timed for 10 seconds and I cascaded that with one time for 20 seconds. Why would I do that? I just have one time for 30 seconds, right? You understand? But all they was trying to do is demonstrate cascading timers. So right now, the only reason I would really cascade timers, if I couldn't put enough time in this one, right, to meet my timing demand. So that's why I'm saying most of the time you see cascaded timers is they're using to set different things, right? You understand? So like run the motors forward for 1 minute and then stop them for what? 2 minutes, and then run them in reverse for 5 minutes. Well, what you would do is you would do what? You would cascade them. You'd have the first one, you would tell it to run forward. You'd bring in the run coils, right? You understand? And then on the timer off, you'd turn both the run coils off, and then the other time you would switch on the forward, the reverse coils. Or coil. So that's normally what you see cascade timers. But like I said, in this class, one of the goals for us to do is to try to reduce the number of rungs in a program. If we can reduce the rungs in the program, what have I just reduced?
The amount of inputs,
the amount of memory that's used by the program, plus probably what? The speed of the program execution, because every rung has to be scanned, right? You understand that? So the less rungs I have in a program, then the faster the scan will be.
There's no kind of like Boolean math or whatever laboratory program.
What's that?
You know the Boolean algebra, no kind of algebra.
Not for timers. So for timers, we can do Boolean algebra for inputs and contacts, ands, ors, and stuff like that. But you can't do a Boolean algebra for a timer. In fact, even in motor controls, we can't do it. In motor controls, even in that we don't have Boolean algebra. So basically, we don't have Boolean algebra for outputs. We have Boolean algebra for what? Well, control. Yeah. So anything inside this over here, we can represent this as a Boolean algebra expression. Anything over here. The outputs are not Boolean algebra. So what you're doing on Boolean algebra, you're trying to reduce the amount of devices that's required to make a rung true, right? That makes sense? Good question. And we literally don't get that into it much in this class. Even in the intro to PLCs, we don't teach that very much, right? You understand? Huh? What's that?
Reduce the amount.
Inputs or rungs too. Eventually, you might figure out that those inputs mean nothing to the operation of the system. So your output, so you'd say this, and this, and Y would be the output when the rung is true. And so we did that in our class last semester. The guy gave us a logic diagram that I realized right off the bat could be what? Reduced. And then when we reduced it, we realized that one of the switches wasn't even required. So it was a 3-switch circuit, right? You understand that? And then when we set up the Boolean equation for the circuit, and we didn't have the class did it, I just did what? I just showed the class what the power of Boolean algebra is. You'll learn more Boolean algebra in digital, and if you take digital. So we don't really try to do a lot of that in PLCs because it takes up so much time. You know, you can take up a long time just on Boolean algebra, and then you don't get through it learning how to program PLCs and that kind of stuff like that. So that's why we don't do it. Because we know in IoT you can take digital, and also on the AUT is an option. Digital is an option. So if you want to learn more about Boolean algebra, then you take one. Digital. This is not that. This is not that class. We introduce you to it and show you the power of it, right? You understand, and give you a reason for learning it. We don't use Karnoff maps at all. I hate Karnoff maps. Well, Karnoff maps is neat as long as you don't get above 4 inputs, because it's a square. So if you use 4 inputs, that's 16 blocks right off the bat. If you have 5 inputs, that's 32 blocks in your Karnoff map. If you add another input, that's 64 blocks in your Karnoff map, right? You understand? So Karnoff map is about as useless as truth tables. So we use truth tables to show you how things work. But if you had a digital gate that had 8 inputs, that would be 256 combinations in a truth table. But it would be simple to have 8 terms in a Boolean equation, right? You understand that? So that's why I like Boolean algebra, because it's just cleans it up, yeah. And that's the biggest problem there is, and you can see patterns. Once you take algebra, you can see repeated patterns, right? Real easy when you assign those things letters. So what did I put on here? An off delay timer. Same one, preset. We're going to download it. We're going to switch to run. And basically what we're doing is we're watching the off delay timer now. So I don't even need to load these. So I'm going to start timing. So notice the off delay timer did what? Nothing. Oh, I'm sorry. There we go. So notice when we come up here and we enable it, so here when the rung is true, now we're talking about the off delay. Let's go look at that. So you're right, I'm sorry, it's a non-retentive. But if the rung is true, what's my timer doing? Nothing. Right, you understand? Because it's not an on delay timer, it's a what? Off delay timer. So what the off delay timer is looking for, it's looking for this rung to become what? False. So that means I'm gonna come up here and make the rung false. And what did the off delay timer do? Start a timer, right? And it's a non-retentive timer. So it means if I make it false, it goes back to what? 0. When I make it true, thank you, Jeff. Thank you, Jeff. It goes back to 0. So when will we use off delay timers? When do you run in off delay timers in live? Do you ever run into them in live? Cars, I have all kind of off delay timers on your car, right? You understand? So when I open my door, my headlights come on. When I close my door, what happens? Starts timing, right? You understand? Turns that off. You run into them all off delay timers a lot, right? You understand that? So in real life. So you can understand why we need these. So an off delay timer starts timing when the rung is what? False. An on delay timer times when the what? Rung is true. A retentive timer does what? Yeah, it holds the accumulated value, right? And the only way you're going to get rid of this guy is to do what? Yeah, you have to reset it with a reset instruction. And that's timers, guys. So watch our registered bits we have available to us. One of them's not shown. Enable. Timer timing. What's the difference between the timer timing and the enable? Yeah. While it's timing, this guy is true. If that rung is enabled, this guy's what? True. So this guy's going to be true even when it meets its time, right? You understand that? Yes or no? And we're only looking at one timer. So right now, that timer up there is enabled, and it's what? Time. It met its value, right? You understand. But the rung is still what? It's still true or enabled, right? You understand the difference between those two bits? Yes or no? And they are bits because they're what? One binary digit, right? Everybody okay? Any questions? Okay, counters. I know it's almost time to go to lunch, but we can start this. Counters. Let's tell us what we know about counters. Now, all we have, on RS Logic, all we have is 2. We have what? Count up, count down. So we could make an up-down counter, but we'd have to combine these 2, right? And we'd have to use some math too, so we'll get into that later on. So this is pretty similar. So here, the only difference between Logic Pro and RS Logic is if you're going to open up a new project, what's the first thing it's going to say? You want to save the one you got. RS Logic Pro don't do that. So what I'm going to fix to do is I'm going to lose this right here, which is no big deal. And we'll use the 1000. And then we'll come up here and insert a rung. Start off with a push button, right? And then the first counter we'll use is an up counter. Did I go past them? Yeah, they're right here in the front. CTU, that's the abbreviation for up counter. And here's our registers. So what's the first thing? What's the first thing we need to do? Sign in an address, right? And what's the technique, guys? So we start off C5 : and then we put a number up there, right? And then what's the next thing we need to do? Preset. We're going to put a constant in there first. This is what we want to count to. In the accumulator right now. So the accumulator is going to be, start off at 0. And then we'll come up here and we'll look at these guys so we can know we can monitor those bits. Download, run. So here we go. We'll come up here, start counting, right? So notice this guy here, count up. Yeah, it goes to enable, but it's actually just count up. Okay. In fact, that's the way you would address, I think, is at the CU bit. And then it comes up here, it gets to 13, right? And then it came up and said it was what? Done. Right? You understand that? Okay. But what happens here? No, it only goes to negative if you get up to 37,767.
Mr. Ryder, that push button was the switch. When you click that switch, it's just gonna count one, and that's it.
Yeah, I mean, we can do that if you want to. So I'll come up here and change it over to a switch. So what it does is it only changes at a transition. So here it changes, and some of your PLCs give you the ability to set the transition. By default, this is when it goes what we call from a low to a high. So only on that edge does the counter count. Okay, understand it. And that's usually true on a lot of your digital counters. We call them edge trigger. So notice I can leave that sucker counted. I can leave it down there forever. How many times did it count? So the only thing it's looking for is that transition. We call it edge trigger. When that input goes from here to here. It don't look at anything else. Right? You understand? So this guy here can stay high for how long? So what I have to do is I'll have to drop it back down, right? And then the only thing it looks for is what? This. Yeah, the rising edge. And we call it an edge trigger count. So we do have edge trigger counters. In fact, a lot of digital counters are edge trigger. So if you ever look at a digital symbol, you see that little guy right there. Now that means it's what? Edge trigger. If it comes straight in, it means the guy's looking for this. If you put a little bubble right there, what is that? Yeah, it's looking for that guy right there. And I've seen in Siemens, you have the ability to set these things up to look for the positive edge or the what? Negative edge. We don't have the ability to do that right here. No, I guess we could. We could change this to a normally closed contact. And then it would be true when it was false, right? Okay, so what's the problem here? So we come up here. It's just easier for me to use a push button because yeah, so this guy, if we want it to go back, and how far would it count up to? Let's see if it does that. Let's see if the Logic Pro does that. So let's go off the program. I set my accumulator to 760. Oops. And we see if this guy picked up on this. And then we'll come up here and we'll download it. So this is what would happen in the real PLC, but we'll see. Oh. Hold on. We'll take care of that. Oh. No, it's not time yet. We got time. Yeah, I'm gonna just move it. That powerful move instruction. So I'm going to set up a constant. I'm going to come up here and say, so we don't want our preset to be here. We want our, I guess it won't stop. We're okay. So we're going to set it to a preset. We're going to use 37,758. 37. And my destination, I'm going to put it into C5 colon 0 dot accumulator. It is 32. But we'd already started off bad, right? I should have known that. Okay, so let's download it and see if it goes negative. That's all we're trying to do. Yeah, that's another. Okay. No, I didn't. What's it doing now?
Keep going down.
Yeah. So it didn't. Like I said, it didn't surprise me. Well, let's see. No, this is probably correct. Y'all go ahead and let's break for lunch.
I'm really interested in the internship over there in Alabama.
Oh, how could you download it? You have to give it to us.
How many you do?
It doesn't pay for your school.
I don't usually take that.
It pays for your, they pay you what you work.
Yeah, that's all I'm looking for. Right now I'm on 2 days a week, Tuesdays and Thursdays. The rest of the days I have free. So Friday, Saturday, Sunday be perfect.
Yeah, that's the only thing they have available now, Friday, Saturday, Sunday that I know of.
Yeah, that'd be perfect. You know what they pay?
Now, guys, the down counter is kind of weird, ain't it? So the down counter, what we normally do, let me figure out which button resets it. That right there. Oh. It don't wanna. Is that me? Sounds like me. It's a little ATR. It does it everything. It'll stop.
You just get down and back off. Yeah, okay.
That's mine too. Oh, someone got up against it in my pocket. So the down counter, let's see if it resets now. So let's choose the reset. Okay, it did. So normally, notice the down counter. So here's the down counter. And automatically, normally we preset it with a what? With a negative number. We're going to use a constant. And it's automatically done, right? Because this is greater than that. So as long as this is greater than that, we get it done. This has to go less than that for the done to go off. Right? Y'all understand? It's kind of strange. If you say, yeah, it is, that's true. So here's my count. I'm counting with 0. So -1, -2, -3, -4, -5, -6, -7, -8, -9, -10. Well, -10 is not greater than that. Y'all understand that? So it still says it's what? Done. So what we have to do on the down counter is our number has to be more negative than that number right there. Right? So what that means is we have to go what? 1 extra count. That makes sense. Kind of strange, right? So normally, if we're going to preset it, we'll preset it with what? There you go. Unless I could do something with this guy. Yeah, so we could trick it out. So what we'll do is we'll insert another instruction in here and make it act like a down counter. So what I need to do, if I'm on down count, is I need to set my preset to what? 0, y'all understand? And then set my accumulator to some positive value. That makes sense? Okay. So if we wanted to look like what we envision a down counter to be, so what am I going to do, Rich? I'm going to come up. Well, that's the same thing true. That's like saying it's how many up counters you need, right? Yeah. Understand? All I'm just showing you how you can make it more logical, So we'll just put another button in here. Which one? I'm going to use 15 down here just for the heck of it. So I'm going to put input colon 15 slash, I'm sorry, not 15, 1 slash 15. By the way, if you had concerns about what you were supposed to learn in PLC 1, then you need to make an appointment with Miss Wilson and then go. That would be your next step, right? You understand that? I think Cece or Christine, she is pretty good at this, and she likes to tutor. So we could probably, and she said she would be willing to do that, guys, if y'all could arrange a time where y'all could all meet and then let her try to get y'all up to speed on what you should have learned in PLC 1. Okay? But you got to let her know and try to set up a time. They usually do it. So you can't split the time. You'll have to do it as a group. So y'all can't have her out here 4 days a week, But she's more than willing just to get y'all, or even if you took PLC 1 from me, if you want, if y'all want to get together and go over that, I really like that. We all could get together and go over that, and just discuss that, and even the rest of y'all might be able to help some of these individuals get caught up to where they're supposed to be. But the next sequence, and that's the sequence. If you've got any concern about a class, there is a procedure that you're supposed to follow. Okay, y'all understand? I cannot do anything. Y'all understand that? I'm just an instructor. Everybody understand that? So the first step you're supposed to do is talk to your instructor, and probably y'all did that. The next step would be to make an appointment and talk to Miss Wilson. And then either she can resolve it, or we can submit go into the college website and do that concerns. And she'll probably have you do that anyways, just because we can have a documentation, have a valid document of what's going on. So y'all understand that step? And that's any class. Any class you have a concern about, whether it's an English class or a math class or a PE class, is there's a procedure set up so y'all can, get a resolution of some concerns you have, if they're what? If they're legal concerns, yeah. You can't say, well, I got a concern because I failed this class, but I only came twice, Well, see, that wouldn't be a legal concern, right? Because you deserve to do what? Fail it. So it's got to be a legal concern. So y'all need to really look at that procedure. So odds are the first one you probably met a little bit, but what y'all need to do is make a appointment with Miss Wilson if you don't want these concerns to pop up for other students down the road. Miss Wilson said she would even be willing to teach classes in the afternoon too. But I think Christine can probably help y'all out a lot and probably do and get y'all up to speed on where y'all should be. So we okay? So let's use we're going to stick a move instruction in there. I have a habit of doing that. I'll come over and hit move and I try to pull that down there. I'm sure none of y'all do that. So what we're going to do is we'll just try to reset our down counter with something. So what I'm going to do is I'll just make up a number. Let's say I'm going to like 15. And what I'm going to do is I'm going to come up here, my destination, I'm going to put it in C5 Ridge colon 1 slash, dot ACC. Didn't like that, dude, because I put it in the wrong place. C5 colon 1 slash, no, dot ACC Ridge. Thank you.
So that's the hex number there,
Yeah, this move instruction is interpreting my 15 as the hex number. And you can do the same thing, guys. Y'all see what it did? So it put the number in there, and then it put a what out here, and that lowercase h. So that means it will interpret it as a hex number.
Didn't you just say a while ago that it only, all those outperforming words in binary, how did it interpret it as a hex
Well,
number?
the problem is, and we talked about this before, is that a computer understands that very few people, we could specify binary. The preferred base, when it displays binary, is it's going to display it in hexadecimal, even though it's a binary number, right? Y'all understand that? And I think what I did is I went in here and showed y'all something that's available that a lot of y'all didn't know about. It's in accessories. So this guy here uses addresses, and the addresses are binary. Y'all understand that? But can't do that there, Rich.
I guess I just meant, I thought you specifically mentioned that earlier in the class today.
I don't remember that. If I did, I was
You're talking
wrong.
about when the BCD was interpreted as
Binary.
But there's a discussion of the original BCD.
Yeah, but it displayed it in decimal, right? You understand. So what my computer does is it's going to display it in a base that's easy to, and displays. So a while ago when I inputted for my input switch, when I came over here, I know what you're talking about now. So when I came over here, these switches are BCD switches.
Right.
But when I inputted that number, so this is what was happening. So when I came over here and put this would be a BCD 10. Okay, you understand? This would be BCD. But when I entered it and it popped up there, it came up and said it was 16. So my computer interpreted this binary, and they interpreted this when it transferred it up or and displayed it as the actual number. It interpreted this, even though it was entered as BCD, it interpreted it as what? Binary. And that's what we was talking about there.
Displayed it.
It displayed it as a decimal. No, it displayed it as a decimal number. It displayed 370 something up there, right? You understand? Because I was putting in, I think 107 or something like that, and it popped up and it was 300 and something. Because why? It interpreted it as a binary number, and when it displayed it in decimal. That makes sense? And I don't know why this displayed it in hex. I didn't ask for it to. For some reason it did. It didn't do it up here, I don't think. Well, I don't know. We can't see the destination. It didn't interpret it here, though. It's just that here, Logic Pro interpreted this number as being what? Hex. So that's decimal. This is displaying it in what? Hex. So right now the accumulator, so we'll download this. We'll switch it to run. Now this is switch 15, right? So I'm going to switch 15. And then my down counter, I need to reset it first, Rich. Or it won't make any sense. Okay. Did it reset? My reset is what? 2, right? Oh, we just got it. There we go. So they reset. And then I'm going to take my down counter and I'm going to come up here. It didn't reset. Oh, I'm sorry. Well, this is what I gotta do. Sorry, guys. Let me go offline. I know what I need to do. Oh, this is what I do. Now I'm gonna change the preset value to 0. Yeah. And then we'll come up here. So we downloaded. There's this counter right here. It's on. Yeah, it did. So it's displaying both bases right here. So let's see what it's doing now. Now it appears to be counting down. All right. And of course, the problem is it's still going to have to go one pass, 0. So the down counter has to go what? It's got to be more negative. But what we're doing here, now it appears to be a what? Down counter. So you see how I set that up? I did what? Yeah, what I did is I moved so I loaded this I loaded this with a positive 15. I set my preset to what? 0. Everybody understand that? And now when I come back here and do my count, which the down counter is 0. Yeah, I'm just going to have to go to the -1. So the down counter is looking for it to become greater or more negative, right? Before the dumb was count on this count. So that's just one method you can do. If you wanted to figure. If you don't do that, then what's going to happen? Your preset is going to have to be what? Negative, right? And your accumulator is going to have to be 0. But notice we have access to both the what? Preset and the accumulator register, just like we do on the timer. So my accumulator, see how it's addressed? This would be C5 means what? Counter. This would be which counter. Dot means it's a word, right? You understand that. And then that would be, means I'm changing the contents of that word. Okay, and how big is the word? So each binary each binary digit is called a what? Bit. A group of 4 bits is called a nibble. A group of 8 bits is called a byte. A group of 16 bits is called a word. 32 bits is called a double word. That's kind of true. That's what we learned in these guys. But what does RS Logic's called a 32-bit word? Long word. So RS Logic calls it a long word. So that's counters, guys. So what type of counters do we have? Up counters, down counters. And the world famous move instruction, which is really, really powerful, because what we can do is we can take these guys, instead of using constants, we can change it so we're using variables. So we can change our count up, we can change our count down, we can change our timers, we can change our presets or our accumulators. We can do all of those. Now, what's the bits? We have very few bits with these. We got 4 bits on these. What are these?
Sir?
4 bits in the status register that you did. Yeah, the overflow. I don't know if this. I'd have to look at it in true. So let's load this count. What? What's that? It's a bit. So if this guy counts up to 32,767 and it tries to go to 768, then what does that mean we have? We have an overflow. So an overflow is one of our status bits, right? If a down counter tries to count greater than 32,768, then we have a what? Underflow. So this guy has an overflow. I'm sorry, this guy here has an overflow, and this guy here has an underflow. Now, what I've done here is,
So that cumulative, that -1 is in an underflow at this time? Is that what you're saying? I don't think I quite.
no, you have to go greater than
I just didn't understand what you meant by
or
underflow.
less than. So our positive counters, we get an overflow if we try to go above what? A plus 32,767. If I go, it has nothing to do with the preset. It has nothing, understand, this is the accumulator. On the down counter, my underflow, overflow.
OVU?
What's that? UL?
UV.
UV, I think. We'll look and make
Is
sure.
it?
UV.
Then if this accumulator goes greater than this, 32,768, then we
Okay.
get an underflow.
Thank you.
So it don't mean you completed the count. Understand, I don't have this set up for this one, but here's the overflow. Here's the overflow right here, right? Y'all see that? And where do I load this guy at? I can't remember. We switch one, right? Okay. Okay, and then we'll come up here and we'll start counting this guy, which would be 0. Now here's the overflow right here, and I've got it set up to turn this light on right here, right? Or this LED here. And my count is 1. Oh, that's not the count, that's the load. Here's the count. 762, 63, 64, 65, 66, 67, 68. And what did we just get? Overflow. Which means I've exceeded the range of my signed number, right? So I was wrong when it says it goes negative. That's right. It just indicates that this, if I'm using this as a signed number, then I just did what? Oh, yeah, I exceeded the range. If I put one on this counter, then we would get an underflow if we did what? If we got less than or minus 32,768. Don't y'all love those signed numbers? So what indicates if the number is positive or negative?
The up or down count?
So we'll come up here and I'll bring up my calculator and I'm going to put it on programmer's calculator. Okay. And what this right here, this is showing me my binary equivalent right here. Okay. So what I'm going to do is I'm going to come up here and put a 1 and I'm going to make it minus. What happened to the binary number? I think turned to 1. So what we do is, when we're dealing with this number system, we call it 2's complement, which we'll learn more in detail. If you look at the most significant bit right here, if you see it as a 1, it's interpreted as a negative 1. So I can put any positive number in here into the range of this guy, and this guy's got a big range. So I'm going to put 35, right? Oh, not minus 35, but 135. What you notice about the most significant bit for any positive number, this right here will be what? 0. For any negative number, this right here will be a 1. So what we're doing is we're sacrificing one whole bit. And we're not talking about a bit down here. We're talking about 2 to the 63rd, right? Y'all understand? This is the big guy, right? You understand? We're sacrificing this to indicate the what? The sign of the number. So that's why it splits in half. But the problem is, if I come over here and put 0 in here, so there's 0. If I looked at this, what would it think it had?
Positive number?
But 0 is what?
Nothing.
It's nothing, right? You don't understand. Now, if you don't understand 2's complement, that's okay. But this thing uses the technique called 2's complement. So that's a -1. So here's a 1 minus. Look at all these guys. If I put a -2, see what happened over here. So it's weird, and I can show you how to do 2's complement. It's really neat. But what we got to do, that's not a -2. That's 12. But that's okay. Let's just change it over signs. So look, we can change all these combinations down here, right? Understand? But what we're doing is we're sacrificing this bit right here. So I can, with 16 bits, I can represent 65,536 combinations. This guy right here is 32,768 right there. I just sacrificed that, right? You understand? To represent the wall, to represent the sign. So what that does is when we use 2's complement, we take the maximum range that we've got, and then we divide it by 2, right? And then we drop 1 off for the positive, and 1 of that. Because 0 occupies one of the positive slots. And that's why these signed numbers are limited to 32,768. I'm sorry, a minus 32,768 and a positive 32,767, right? Because 0 occupies one of the positive slots. Does that make sense? 2's complement is neat, but so any questions on counter? Yes or no?
Not right now.
The move instruction, are we okay on this guy? So what do we have? What's the source? That's what we're moving, right? You understand? And what's the destination? That's where we're moving it to. This guy has got to be an address. The destination has to be an address. This guy right here has got to be, it could be an address or it could be a number, right? You understand?
Yeah.
So the source can either be the address of the contents of an address that we're moving, or it could be the number itself, right? Y'all understand the difference? This right here, the destination, right? You understand the destination, it's got to be a what? An address. That makes sense? Yes or no? Your preset, these can be constants or they can be variables. Your accumulator can be a constant or a variable. All right, understand that? Everybody okay? But these have got to be numbers. You understand that? Makes sense. And so that's what we're going to do. We're going to run into a bunch of sources and destinations as we move through this semester. And we need to understand what the requirements are for the source. Usually the source can either be a what? Usually the source can be a number or an address, right? The destination address. So if I add 2 numbers together later on, then my 2 sources, my source A and source B, they can be numbers or an address that contains the numbers. But if we add 2 numbers together, we're going to have to put it somewhere, right? So we'll have a what? We'll have a destination. So when we add stuff, we'll have a source A, a source B, and then we'll have a destination. The destination is always going to have to be the address that you want to put your answers at, right? Does that make sense? So now you know math. So if I multiply, I'm gonna have what? A source A, a source B, and I'm gonna have a Y. That's what- So what we're gonna do, Tuesday is we'll come in here and just straighten some stuff up. We'll be in lab most of the day Tuesday, and we're gonna do one of our timer labs. I don't have my book up here. I think it's. Now we're gonna have to look. If you got the new one, I'm sure they have the same labs, but I'm gonna have to see it and figure out which lab is off. Is that one split up in activities, just like the regular? And then, your counter timer labs, these are, you can look at the labs, they're really neat. So we start off with, counter timer labs. So in PLC 1, you had counter labs and then you had timer labs. But what we're going to do is we're going to start off with what? Counter timer labs, which will be, in this one, it's back here in section 9. Which is pretty good. It might do that in the new book too, if it lines up with the chapter numbers. I don't know about that. Yeah. Well, what we're doing is we're looking at the very end, so that they have a section on counter timers, right? So in PLC 1, what you were supposed to do is you were supposed to do counter labs and then timer labs. And then what we do in this class is we do counter timers, which basically combines counters with what? Timers. And the activity, are we okay? Oh, good. That's great. Glad that.
9.3 begins the PLC counter and timer instructions, and it's on page 179.
Yeah, but what we're going to be doing is we're going to be down in like 9. Yeah, we're in the counter timer instructions, not the timer, not the counters.
Right, like if you look at page 183, it says PLC counter and timer instructions. No, no, it is. Right in the title at the top.
What's that? By the way, another thing that we're going to do is that this guy talks about a master start-stop switch. How many master start-stop switches do you think you're going to run into? None. Probably none. What we do is what they do in industry is we use what we call a start-stop circuit. And I've showed y'all that several times in this lab. Some people call it a memory circuit, some people call it a seal-in circuit, some people call it a 3-wire circuit.
I like
But what we'll do is we'll start off with a stop button. And we're going to give it a name, right? Input : 0/0. And if this is a stop button, it's supposed to be a what? Normal stop. And like I said, and then we're going to start off and we're going to put a start button. Huh? Now we're going to use an examine if closed. And we'll call this stop. By the way, over in Germany, they put the stop after the seal-in, which is strange. They could never tell me why when I asked. By the way, RS Logix, when you put your symbol, Logic Pro, it puts the symbol name on the bottom, but on RS Logix, your symbol name goes to the top, right? And every time you enter an address, it's going to ask you to enter a symbol. Logic Pro, you cannot use the symbol name as an address.
So you can't do like PB1
Yeah.
and
In RS Logic, once you assign a symbol a name, then instead of typing in the address from then on, you can use the what? You can use the name, which is really neat, which I really like. because it's a lot easier for me to keep up with symbols than it is for names. And they let you set up that. Logic Pro don't let you do that, but RS Logics lets you set up everything before you even start. So you go down to that column that says symbols and symbol and addresses, and you can enter everything before you even start. And then from the very start, you can enter what instead of what. And so symbol names instead of addresses. We'll call this guy here start. And then what we'll do is we'll come in here and we'll put a down drop or a branch, whichever one you want to call it. I've always called it a down drop. And then we'll put another contact in here we're not ready for yet. And then we'll come up here. But if you had assigned a symbol name, you could have done that. So we'll come over here and we'll use one of our outputs. No, normally what we do on this guy is we don't need an output for this guy. This is just a start-stop station. What we'll use is we'll use one of our B3 registers. So that's an internal relay. And in PLCs, inside a PLC diagram, you're going to run into a lot of internal relays. So you don't have to assign contacts to an output port, right? The only time you should ever use an output port is when if you're gonna do something out there, right? If you're gonna turn on a light, if you're gonna bring in a relay, you're gonna start a motor, then you're gonna have to assign it an output port. If we're not going to use something physically to turn something physically on the outside world off and on, we use internal relay. Y'all didn't talk about the B3 register? We have two. Some PLCs have B3. All of Allen Bradley PLCs has a B3 register, but some of them also have a what? A B10.
Oh, yeah.
Yeah, B10. But all of Allen Bradley PLCs that use RS Logic has a B3 register. And we use these primarily for what we call internal coils. And what's that mean? They don't generate an output. They don't turn on a light. They don't start a motor. They're just strictly for control. Y'all understand that? I'm giving you a headache, Austin.
Oh, I'm so tired. I made another call.
You got one?
Oh, man, yeah.
I'm
Does that
listening.
work, though?
No. The stop button's supposed to be normally closed.
Yes.
Y'all understand? The stop button's supposed to be normally closed, but not the contact, not the logic. We'll look at that. So we'll start off. We'll start off by making it normally closed and see what happens. So over here, now listen up. So over here on our simulation, I've lost it. So this guy right here, if it's my stop button, it's supposed to be a normally closed, right? You understand? So I'm going to change it to a normally closed. But over here in my diagram, I'm going to use this symbol right here. Okay? You understand that? And then wait. Huh? It's wrong, right? It's wrong, right? It's wrong, right? On purpose. And we'll assign this. We want to turn on a light bulb with this guy, so we'll assign it to one of our outputs.
It didn't want to be assigned.
No, I must have put. Oh, I'm sorry. No, it's not internal. It's our first output port is 2, right? Okay. Okay. So what we're going to do is we're going to go ahead and download this. I have a normally closed push button. And why is normally closed push buttons required for a true stop button? Well, if we break a wire, we need this thing to stop if we break a wire, right? So this, this, and then honest to goodness, this only comes into play now. So I'm gonna come up here and I'm gonna download this. And then I'm gonna run it. What did it tell me?
You're running.
Oh,
You're
okay.
downloading it.
Okay. Yeah, I do. Now, what would have happened if I was using Logic, RS Logic?
It would say your error.
So, what you find out is Logic Pro lets you get by with a lot of stuff.
Not very
Well, it's
When
it's
you're
not-
learning, it's alright, but
well, not even when you're learning, because I can put two coils out here, and if I energize them, they both become true on Logic Pro. Well, Logic Pro, and I did it again. 2/0. We'll get it in a minute.
Eventually. Alright, run.
Yeah, I did that too. I'm getting the 1000. Okay, guys, y'all take care of me. Is that okay?
Yeah. Now run.
So this is my start button. I lost my symbol.
It's not starting.
Yeah, so what we got? So notice this guy right here. So right now,
the input or the,
so what do we call this one on the left? This is an examinative open.
oh,
This is an examinative close. This guy is false because it's not open. This one only becomes true when so this is an examine is closed. This is an examine if open. This one is true when it is open. So I could come over here and I could change this to a normally open push button and it would work okay. So now it's open. Now it's open and it's true. That's an examine if open. This is an examine if closed. Examine if open. So this guy is true when it's open. This guy is true when it's false. I'm sorry. This is true when it's closed, right? You understand? Okay. So now it appears to work and do what it's supposed to do. So this is a memory circuit. Now it seals itself in, and this would be my master switch. But what's the problem? My stop button is a normally open button. So what would happen if I lost that wire coming out of that button right there? What happens all the time? You can't stop, right? You understand? So what we have to do is I want to use an examine if closed, right? You understand? Now motor controls, this is the way it would be. We'd use a normally closed push button over here, but this is not controls. This is PLCs, right? You understand? Now I can change this to a closed button, right? Y'all understand? Okay. And you have to cycle and then go to run. Now my stop button works. This is an examine if closed. My contact is closed. Examine is closed. My contact is closed. So this is true, right? You understand? So what you're going to have to do on the 504s is you're going to have to use one of these buttons as your stop button, and you're going to have to put it up all the time. And that way you're simulating a normally closed button, right? You understand that? And that will be your stop button. On your 1000s, you're going to have to use one of your selector switches. So the only thing you got here on 0, 1 through 1, these are all normally open. We do have this selector switch that I can do what all the time. I can turn it on, right? You understand? It simulates a normally closed push button. In industry, you see very few, you see a lot of normally open button. And then from then on, guys, just about every other push button that you'll run into in a PLC circuit is going to be a normally open button. And you just call it what you want it to act like, right? If you want it to act like a normally closed button, then use an examine if open. If you want to make it act like it, then the only time you really are concerned is when you set up this stop circuit. The stop circuit, the stop button is supposed to be a what? A normally closed. Why? Because if the wire breaks, which happens all the time, you would not have the ability to do what? Stop it. But if we use an examinative close and the thing breaks, right, you understand, then what's going to happen? It's going to stop. It's better to have something stop than not have the ability to stop. Right, you understand? And it's like your car. You'd rather for your brakes to be locked up than the brakes not work. If your brakes are locked up, then you can't drive. If your brakes don't work,
Can't stop.
then you can't stop, right? Well, that's why we have to do that. So we're going to have to simulate this. We don't have push buttons. So in industry, you see very few switches. You see selector switches, but you don't hardly see any switches like this. Because you got these guys that's got gloves on, right? Accidentally hit these things is not good, right? You understand? So they have these push buttons. They're in shrouds, so they're flush. You literally have to do what? Push your finger in there and press them. And that's why and then now you can make them green, you can make them red, right? You can put legends above them. You can do all kind of neat stuff. So the primary thing that we're using in industry is push button. Selector switches you'll run into every once in a while where we can set up what we call a run jog circuit. But anytime it says a master switch, this is the circuit I want right here. Because you're not going to run into a circuit that's got a master switch. You're going to have this guy right here. Right? You understand? So now I just have to go over and do what? Press a button to start it and do what? Press another button to stop it. You understand? So anytime it says a master start-stop switch, let's see how this says it. This says a master switch is the main start-stop switch. And that's still true. Well, that's not true. We're using how many switches? 2. But understand B3. What's B3? So, does this guy generate an output? No. So, in motor control, when we start dealing with very complicated motor control, 90% of the control circuit is decision making. Just that this is before that, and this is before that. And if I don't need a relay to generate an output, I'm not going to sacrifice an output. I'm going to use an internal relay. And we have 2 available to us in some. This one we have only the what? B3, and then some have the B10. Now where can you see that information at? In your project tree. So when you come over here and look at your project tree, right here, this shows you everything you have available. So I know I have what? Outs. I know I have ins. There's my status register, my S2 register. There's my B3 register. So this PLC does not have a B10. If your PLC supports a B10, it'll pop up in this list. And in that way, how many bits do we have? Well, we got 255 of these things, and there's 16 bits inside of each one of those. So we can have a ton of what? Internal cores. I mean, a ton of them. But that's what we need. In motor controls, we call these things control relays. A control relay is a relay whose contact never goes into the power section. All its contacts are where? Inside the control. So if you was in motor control, if you was converting a line diagram, a electrical line diagram, every time you see a control relay, what would you do? You'd use an internal contact, right? That makes sense? So you're okay on our stop station. And then, of course, what we would do is we'd use this contact one of two things. If it says you have to look at it, it says, okay, if we want it to enable or disable everything, then what might you have to do? You might have to put that contact the first in what? In every rung, right? You understand? But if you got a timer and then the timer is controlling everything, you might be able just to put it in the timer circuit, because if the timer's disabled, it does what? It disables everything down below it anyway. Y'all understand that? Any questions there? So we're going to be looking at, I'm looking for one that has both timers and counters in it. 4 times the motor, press it right, motor runs 1, turns on 5, there we go. So we'll do activity 9-7. And while we're telling you this, so y'all can go ahead and work on it at home, right? Okay. Because step 1, 7 act, so it's going to be a 9-7 PLC 3. On this book, it's on page 195. I don't know what page it is in yours. Yes. And then we're looking at activity 1, and it starts off, the black switch is a master reset. No, that's not true. That's not the one I want to do. Thank you. This is the logic for that. So we're looking for one that's got both timers and counters in it. Okay, so let's do 9-5. PLC counters and timers 2. On this page, it's on 187. And we'll do activity 1. So what does it start off with? The first step, y'all see that? It says what? It says use the master start switch to turn the system what? On and off. And to reset the timer. Right. A timer, but then it says when anyone stops it, let's see. But it also says close the thermostat switch to start the lubricating pump for the motor 1 and number 2, lubricating the pump for the motor 2. Motor 2 is running, their lubricating pump is off, pump is lubricating, pump should be. No, that's not the one. I want one that's got both timers and counters in it, guys. Y'all help me. But it also has a master switch.
You don't ask too much, huh?
I don't ask very much. On my book over in my classroom, I've got it marked, but unfortunately, I didn't bring it over here. I'm just sorry.
The PLC room?
No, in my office. In the other building. That's another one. 9-3. Yeah, but then it's got to have a timer in there too. Does it have a timer?
Which one? Counter.
If it don't have a master switch, we'll add it. Okay.
Yeah, it has all three.
9-3.
Doesn't it have a switch?
Activity 1.
And a timer, I believe. Activity 3 does.
Huh?
I was looking at activity 3.
Activity 3. I think
Switch
that's.
to reset system.
I think that's
green
it.
push button. The counter and then green palette light to turn on and light off for 3 seconds. Does not describe something that uses a counter and a timer.
Yeah, that would probably be about the simplest we could do. The only thing we're going to do, we'll do so on 181, activity 3. But what we're going to do is we're going to add a what? Master switch to it. Okay? Is that okay? Page 181 in the old book. Activity 3. So this is this is one of the simple ones where we can add timers and counters together, right? So it says you switch one to reset. So that's the reset. But what we're going to add, the first thing we're going to add a master start stop station. Everybody okay there? Okay. Then use a switch to reset it. If the green light, if the green push button is and the red push button are each pressed 3 times, the red pilot light and green pilot light will turn on. The lights will stay on for 3 seconds. So that's both counters and what? Timers. Everybody okay? So which one?
Activity 3 from 9:30.
Okay. So what we'll do when we come in Tuesday, y'all come in here. We'll see if we got any problems, right? You understand? And then we'll go to lab. Are we okay? Yeah. No, we'll talk a little bit about math. The math's not too hard. But this lab shouldn't take very long, and we don't want you to go down there and do one lab later. Are we okay? All right. See y'all Tuesday. Where at?
What?
In this room to start, right?
Who do we lose? Terrence lose? Terrence got? He left and didn't tell me to leave. Yeah, well, he took his books to go to the restroom.
Maybe he's still in a fire or something.
I'll try to, I got one.
Hey, you gotta have some reading material.
I'm going to bed. Don't out.
Don't wait up.
Going home now. Going home now.
Yeah, 3 times.
Here's my,
I'll make it ring 3 times. Yeah. You can't push it 3 times. Sorry. Now this is, you're right, I can push it 3 times and make it ring 3 times. But they want, here they want to do it. I mean, I'm sorry, Ken. Thanks for bringing that up. Yeah, we can, to ring the bell 3 times, you can't do that. You're going to have to do it through a count.
I'm saying like we have to control the calendar.
Yeah, well, what you do is you can turn the light on each time with the push button, but you're also going to have to implement the counter because you want it to do it 3 times. If you just did it with the push button, I can do it 15. That makes sense? Yeah. So your push button can do 2 things. Your push button could turn the light on, but it's also going to increment your counter. And then what you're going to do is you're going to light into the gun contact down here. You press it 3 times, then it does what? It'll stop no matter how many times you press it. So the light will only come on 3 times. Does that make sense? Oh, my leg.